Okay, so this is the self-driving vehicle project that we did. So my group members are Zhuohuan, Anthony, Sandeep, Lohith, me, Abia, Malav, and Aayush.
Before we begin the presentation, there are a few useful words that need to be defined. The first is ROS, which stands for Robot Operating System. ROS is a set of software libraries that we use to build and manage the robot programs. Next is Gazebo, a software that's pretty similar to a game engine where we were able to simulate our robot in a 3D virtual environment. And the last is a neural network, which is a way for computers to learn using a network of different functions to convert input to a desired output.
So our objectives for this project include building a fully functional self-driving vehicle, incorporating ROS control and packages into a simulated self-driving model in Gazebo, and writing machine learning algorithms and building a neural network to properly train our car to be autonomous, and use Gazebo to test our simulated model to run them in a digital environment, and build a physical model at WinLab and test its autonomy in a real environment. Next slide, please. And before we were able to meet in person at WinLab, we started our work in Gazebo Simulator. After learning the basics of Gazebo through tutorials, we built our basic self-driving model and tested it with Ackermann steering, which is a form of steering in which the inner wheels and outer wheels turn at different speeds to avoid sliding. And we drove this simulated model in a digital environment using a Python script called pyop.py, which allowed us to control the car with our laptop's arrow keys and also adjust the speed and the steering angle. And the picture shows the Gazebo user interface, and we control the vehicle via the terminal. The terminal also shows the attribute of speed and the steering angle of the vehicle. Next slide, please. And one of the first things we started working with when we visited WinLab was the 4 RealSense cameras around the model's city intersection. By loading the correct RealSense image, we were able to view points cloud, which is the collection of points characterized by color and position for each of the 4 cameras, and combine them all into a 3D, one 3D image using something called a affine transform, which involves rotating and moving the point clouds in 3D space, and then appending the point clouds together to create one image. And the picture shown here is one of the camera's view in the intersection. Next slide, please.
Midway through our project, when it was finally determined that we would be going back in, a good portion of us started working on a robot car called the Pioneer 3X, pictured here on the upper right, which was compatible with ROS and had multiple sensors that could be used to detect objects around it. Referring to our project objectives, we wanted to incorporate machine learning algorithms onto a robot. This is that robot that we used to accomplish this. The main package that we used to control this robot was called ROS Aria, an interface that could communicate with other ROS nodes, pictured here on the bottom left. Lastly, in order to actually record what is actually in front of the vehicle, a RealSense Steph camera was attached to this top. Next slide.
So as Anthony said in the previous slide, we chose ROS Aria over Aria Coda to control our robot. And we use ROS Aria to wirelessly control the Pioneer and something called ROS Bag to subscribe to both a control topic and an image topic. So subscribing to specific topics means that only the data from those 2 topics will be included in the bag file. And a bag file is just a collection of different ROS message data. So in our case, the bag file only contained data from 2 topics. So the control topic that we used, it's ROS Aria command velocity. And what this does, it gives us the speed of the robot and the steering angle of the robot. The image topic, this is a continuous camera feed from the attached RealSense camera that we chose that was attached to the Pioneer. And we chose to use the compressed form of these images just so that when we recorded the bag file, the file size wasn't too big. So this interface in the top right, this is what RQT bag looks like. So on the left of this interface, this is a control topic. So we use the twist message, and this twist message has 2 attributes. It has a linear and an angular attribute. So the linear speed of the robot, that's the X variable in the linear attribute. And then the steering angle of the robot, that's the Z variable of the angular attribute. And the picture to the right of the control topic, that's the output of the RealSense camera feed. So that's what the robot's seeing as it's driving. And then the bottom, that's just a timeline of, so it shows the two topics on the left and then how long the total recording is. And so this video here, this shows how we trained our robot. So we built a track using some cables we found at WinLab, and we drove the robot alongside these cables, making sure it didn't go outside of the cables. And as it was driving, we had it record both the control inputs and the image inputs and the image feed. And so after this, we took this bag file and we fed it into a bag to image file. And what this did, it converted the bag file into an NDZ file. And then we took that NDZ file and we fed it into the 4 convolutional layers of our neural network. And that's how we trained the robot. So we repeated this process on different tracks. And then to make sure that our robot didn't overfit, we changed the orientation of these cables from time to time, and then we kept training it. So in the future, we'd like to use the depth sensor of the RealSense camera in conjunction with our control and image data. And this could provide us with more training data and also make our robot's steering a lot more precise when driving. So this picture in the top right, this is what the depth camera sees at the model intersection. So that you can see the blue things closest to the robot, those are the people. And then the 2 objects further back, those are model cars. We'd also like to be able to access Rosaria and the various ROS packages without using a remote desktop, which is what we use to control the robot. And we'd like to bypass this step because the process of setting up a remote desktop takes a lot of time. And so if we could somehow bypass this step by using something like SSH forwarding, then this would just be a lot more convenient for the user. Also, if anyone outside of our group wanted to access the RealSense camera feed, we'd like to come up with a way for them to be able to see the output camera feed without having the ability to control the robot, just for basic security reasons. And finally, we'd like to configure ROS ARIA and load ROS onto the smaller mobile robots pictured in the bottom right. These robots also have RealSense cameras attached. So if we could load the same packages that we loaded onto the Pioneer, then ideally we would have all 3 robots driving alongside each other in the smart models city intersection. Also, special thanks to WinLab for allowing us to do this project, and a huge thanks to our project advisor, Jenny, for helping us with our long list of technical difficulties every day, and also just for guiding us along the project. And another huge thank you to Yvonne for helping us with all of our orbit-related problems, and for also being a great photographer.